Hey everyone, we're almost at the end of 2024. I've decided to create a series for VCE Physics Units 3 and 4 course to help anyone doing Year 12 Physics next year to learn ahead of your class and also help you revise over the year. So, I've kind of created a plan for what my series will look like. I'm not sure yet how many videos for each lesson, etc., but I'll be going in order from left to right columns, definitely. So in this video, I'm going to cover the two boxes highlighted. So let's get into it. Uh, Before I begin, just a note on like prior knowledge. With most of this course, I'll assume most of you have done year 11 physics, but I will still go into a bit more detail to help those who might not have done it like this year for year 11, going to next year for year 12. So if you haven't, this course can definitely still help you. So today I'll start with Newton's laws and some basics of motion. From my experience, the first law is the most easily forgotten, since the other two laws are basically formulas. You'll probably ask about this law only in SACs, but it's definitely useful to know for the exams as well. So the first law is about inertia, how an object will not change its motion unless the net sum of all its forces is not zero. We say non-zero because forces have a direction, so it could have a negative force or positive force depending on which direction is positive, because they are what we call vectors. I'll just quickly diverge here for those who have not done year 11 physics. Some quantities like speed and distance are scalar, so they only have a quantity and no direction. But a vector has a quantity and a direction. So like speed is a scalar, but velocity has a direction as well, so it's a vector as well. And force is also a vector. So we have a rocket here resting on the ground, and it's at rest because it's normal force, so the force of the ground pushing up on the rocket, and force due to gravity are both equal. So that's why it's not falling into the earth or flying out. Otherwise, that wouldn't be very good. But if the rocket launches, so we could have two situations here. So when it first launches, of course, there will be a new thrust force. So that thrust force will be greater than air resistance and the gravity. So it starts accelerating. So let's say it could go from 0 meters per second to 10 meters per second. So because accelerating, it has a non-zero net force. It's going up. Its net force is upwards. But also if it's flying, it could be traveling at a constant speed. So its thrust force could be exactly equal to the sum of the gravity force and air resistance. So that's basically the first law. So this applies to constant motion and being stationary. All right, now we have Newton's second law. This is simply F equals ma. I just added this here for on Earth. Your A would be, so gravitational force, acceleration would be 9.81. So that's on the exam formula sheet. So I just made a question here. We can apply this formula too. So we know the car's mass. I've drawn the frictional force and the driving force. So here it's accelerating at, so to so we know the car's mass, acceleration, and frictional force. I put them all here. To find the driving force, the blue arrow. So we need to calculate driving force. So the blue arrow, we would first need to calculate the net force of the car. So that's just m times a. So 100 times 2, that's 200 newtons. I forgot to put the 2 here. So then we can just, let's say the right side is positive. It's a good idea to always uh, determine what direction is positive before you do your calculations. So we can set up this equation. F net equals F drive minus FF. I'll just label them like that. So FF is the frictional force. Uh, so we can just substitute our values in. So 200 equals F drive minus 80. And we can rearrange, we get 280 newtons. But we must make sure our answer has the same number of significant figures as the value in the question that has the least number of significant figures. So that means, like for this question, our acceleration and our frictional force, they both have two significant figures, which is the least number. So we have to actually write our answer as 2.8 times 10 to the 2 newtons. Because this is important for the exam. If you could lose a mark for rounding incorrectly in that little box you write your answer in. But you only get marked down once. So if you make multiple significant figure errors, you only get marked down for 1 mark. So you should get into the habit of doing that as well. So the third and final law is about action-reaction pairs. We'll revisit our rocket here. Let's start with a simple question that teachers and examiners like to put on SACs and exams all the time. So what is the reaction force of the force due to gravity on the rocket? The answer is not the normal force. The answer is that answer is the force on the Earth due to the rocket's gravity. So all objects with mass uh, exert gravity on other objects, but of course it's not enough to move the whole Earth, but it's still there. Now with this other rocket, have a go. So we have the force of the thruster gas on the rocket. So what's the reaction force? Well, that's simply the force on the thruster gas by the rocket. So it's pushing the gas down, which is what propels the rocket up. The hardest thing with these questions is just explaining why the normal force is not a reaction force to the force due to gravity. You can simply say that action-reaction pairs must act on different objects. So for the normal force, it's both acting on the rocket ship, so that doesn't make sense. That's not correct. That can't be action-reaction pair. So in this one, the two objects on the left, the rocket on the left, the two objects are the Earth and the rocket. So time for a couple of questions. I recommend pausing and having a go at each question before I go through it. Okay, so this one asks us to find the force on box Y by box X, or of box X acting on box Y. So first we should always draw what forces we're looking at. So this one, this arrow here. So that's box X acting on box Y. That should always be your first step. So now we can see that the force on box X on box Y is just the force due to gravity on box X. So that's easy. We can just calculate that. So we write, it's good to write the formula, Fgx. Because we know the gravitational acceleration, we just do 75 times 9.81, and we get 735.75 newtons. Of course, this is not our final answer, so we can rewrite that as, because the least number of significant figures is the number 75, which is just 2. So we just rounded two significant figures and put in scientific notation, because, yeah. Alright, so this is the next part of the same question. Here we are given the information that both boxes are stationary on the floor. So using Newton's first law, we know that box Y must have a net force of 0 newtons. It's asking us, what is the magnitude of the net force of the floor acting on box Y? So first we have to draw all the forces. We have the force of X on Y, the gravitational force on box Y, and its normal force of the floor pushing against it. So the normal force, or the force of the floor acting on box Y, is what we're trying to find here, because that's the same thing. So we know F net of Y is 0, because it's not moving. And then we can just write an equation here. Let's say up the page is positive. So yeah, we have Fn, so normal force, minus Fx on Y minus Fg, all equals 0. So with this, we already found the force of X on Y, so 735.75. And then we can just add the gravitational force on Y. So of course that's ma, or in this case mg, using Newton's second law. And we get 2,207 something. And again, we have to round it to two significant figures, as you can see here, as the final answer. Alright, so this is the last question I'll go over before I wrap up this lesson. So here we have Amy driving a tractor. So this question might look complex, but don't worry, it's more straightforward than it looks. All of that is just to confuse you. So Amy's tractor is accelerating by 0.25 meters per second squared. So with these types of questions, you should always remember that the acceleration of the whole system, in this case 0.25 meters per second squared, is the same as the acceleration of each of the individual objects. So that means for pyramid 2, because if I calculate the magnitude of rope 2, that would just be the same acceleration, 0.25 meters per second squared. So we can just use Newton's second law. We calculate the force, the net force on pyramid 2 is 62.5 newtons. Now I'm going to define the left side to the left as positive, and then we can set up our equation. So we get F net of pyramid 2 equals tension of rope 2 and the friction over here, 100 newtons. So we can just rearrange this, and then we sub in our value, so 62.5 plus 100, and we get 162.5. And our final answer is 1.6 times 10 to the 2, because 0.25 has the least number of significant figures. So that's the final question of this lesson. This is the first time I'm recording this kind of lesson, so do let me know in like the comments and stuff if you want longer lessons, cover more content, or like if I'm going too fast or too slow. So you can just give me that feedback. But I hope you found this lesson useful. Thank you.